Hello, my dear warriors. This is your Captain Shreyas. Welcome aboard. Good evening, my dear warriors. Hello, hello. How are you guys? I'm doing good. Thank you so much. Thank you so much. And welcome to the NCERT line by line series. All the warrior pandus start trending. WP. I want to start seeing warrior pandus trending. Yes, WP. Warrior pandus whistle podu. Thank you so much, guys. I'm doing great. Excellent day. So, this series is meant to boost your preparation by, seeing every single aspect of NCERT. And like I said, even in the launch session, that NCERT has a lot of weightage and a lot of coverage in the NEET examination. A lot of questions directly are handpicked from NCERT, even the statement-based questions, sometimes the in-text questions, the solved examples, and so many important tables, experiments, diagrams, everything directly as it is picked up by the NTA for your NEET examination. So we'll be starting off with units and dimensions, right? I hope you guys are all ready for it. Thank you for all the lovely comments, guys, and keep that Josh high throughout the session. And like I said, even during the launch session, this is going to happen for all the subjects, botany, chemistry, as well as zoology. And every day in the evening, that's what we are going to do this. The classes will be scheduled roughly at around 6 o'clock or 5 o'clock or 7 o'clock. And trust me, this is the first time this is happening on YouTube, especially on the English channels. So it's time to begin with the class and start off with units and dimensions with your captain Shreyas, your physics master teacher on the Vedantu NEET English, teaching kids for more than 13 years and sending kids, thousands of them, into their dream medical colleges. Now it's your turn via this particular series. Quickly show your love and support by smashing that like button and subscribe to the #1 NEET English channel in the country. Have you done that? Subscribed already? Very good. Keep the chats flowing. Awesome. And smash that like button. Done? Dusted? Great. Let's move to the concepts now. Okay. I have taken snippets from NCERT and we'll be seeing all the important pointers one by one. Now, if you see the first paragraph of units and dimensions, the chapter 1, it talks about that measurement of any quantity involves comparison with some basic arbitrarily chosen internationally accepted reference standard called as a unit, okay, which a basic arbitrarily chosen internationally accepted reference standard which is called as a unit. The result of the measurement of a physical quantity is expressed by a number or a numerical measure accompanied by a unit. Although the number of the physical quantity appears to be very large, we need only a limited number of units for expressing different quantities since they are related with each other. And the units for the fundamental base quantities are called fundamental or base units. Okay. See, first few lines they are talking about what is the meaning of a physical quantity and how it is expressed. I have fever. That means, okay, I have high fever, low fever. That is not a physical quantity. I might feel unwell. I am not feeling that great. That is not a physical quantity. I am feeling very happy, very excited. How excited I am. It's not a physical quantity. But what is my temperature? That is something which can be measured, can be given a numerical value. That is a physical quantity. Okay, I'm very excited and I can run. I have a lot of energy and I can run at 20 meters per second. So my speed becomes a physical quantity. But, just saying that, I'm very excited, it's not a physical quantity because there is no number associated with it. So the first part talks about any physical quantity is always a number along with a unit. For another example, I can say my velocity or speed is 20, which is the number, and unit is meters per second, like you can see. Force, let's say, is nothing but 9 Newton. 9 is that number, Newton is the unit. Got it till this point? And they say that there are many physical quantities. So you might think there might be many units. Actually, there are not infinite number of units. We have only certain units because we can express one unit in terms of other unit, which we'll be seeing in the due course of the chapter. That's what they are saying. Now, the next important point is right over here, that the units for the fundamental or the base quantities are called as fundamental or base units. The units of all other quantities which can be expressed as the combination of the base units, expressed as a combination of base units, they are called as derived units. And a complete set of these units, both the base units and the derived units, is known as the system of units. See, there are certain things which are like very basic and fundamental, and other things are dependent on it. For example, when I say velocity is nothing but displacement by time, this displacement and this time both are base or basically fundamental quantities. This velocity depends on these two, so they are said to be derived quantities. Same way, the volume of any cube can be said as side raised to the power 3. This side is our fundamental quantity. This volume becomes our derived quantity. Derived quantity. So same way, displacement being fundamental, what is it measured in? How many meters? So meters is the unit. Time is a fundamental quantity. How do you measure it? In seconds, hours, etc. So they will have fundamental units, maybe meters, kilometers, whatever. This time might have fundamental units like seconds, hours, minutes, etc. So combination of them will then become meters per second, kilometers per hour. Those will become the derived units. Got it? Same way over here, side can be measured in centimeters, meters, kilometers. They will become the fundamental units in which you measure the side length, whereas volume will become meter cube, centimeter cube, cc, ml. That will be the unit of that derived quantity. That is what this particular line is explaining. So when you have a complete set of fundamental units from meters, centimeters, etc., and then derived units like centimeter cube, meters per second, kilometers per hour, etc., so the total set is called as a system of all the units. So that is called a system of all the units. Everybody clear till this particular point? Introduction is clear. We have something called as physical quantities which can be measured. They always have a number along with a unit associated with it. And you have two kinds of quantities, hence two kinds of units. Ones which are very basic or very fundamental, and they are universally called as fundamental, like displacement, time, will come to more of it. And then all those things which depend on them, they are said to be the derived quantities. As simple as that. Now, in the next paragraph of 1.2, which we talk about international system of units. Like we said in paragraph 1, all the units like Newton, what is meter, what is centimeter, they are defined, they are decided and accepted internationally. Nobody cross questions them. When somebody says this much is a meter, yes, we accept. We'll not be like, why this much is not a meter? We do not argue. That is why this first line was important. It is accepted as a standard, else it will not be a unit. Or else I can say, Shreyas Sir's hand is 1 meter. Tomorrow Shreyas Sir grows tall, then meter's definition will change. Correct? Understand. So what happens before Shreyas Sir? What happens after Shreyas Sir? So my hand should be preserved then in a museum. Understand that. Okay. In earlier times, scientists of different countries were using different units, and for historical reasons, we have basically three different types of units in our world. One is called as a CGS, one is FPS, and one is MKS. Now, different parts of the country had different reasons for using different units. We'll not get there, but for historical reasons, we have three different systems across the world which are widely used. CGS is where you measure the length in centimeter, mass in grams, it is weighed in grams, time is measured in seconds. That's why CGS, centimeter, gram, second. In certain parts, like especially UK and all, British system, which is also called as FPS system, length of anything was measured in feet fundamentally. The weight was measured in pounds and the time was measured in seconds. So foot, pound, second system, British system. MKS, also sometimes called as a metric system. Mass was measured in kilogram. Length was measured in meters, so M for meters, K for kilogram. Time was measured in seconds, so meter, kilogram, second system. All right. Now, the most widely used system is basically MKS system. Okay. And right now, do we use CGS, FPS or MKS? Actually, we use a modified version of the MKS system, which is now called as the system of units, SI system. Okay. It is actually in French, but let's not get there. It is just called as SI system or System internationally, the unities and something and all that. Okay, let's not get there, guys. So it is just called as a SI system, which is just a modified version of the MKS system. So what was exactly modified and what was there in MKS? See, in MKS only length was in meters, mass was in kilogram, time was in second. But later on, scientists understood that there are more fundamental quantities like amount of a substance, light intensity, temperature. All these were also considered to be fundamental. They were later on added into the MKS system, which right now is called as the SI system. Okay, so the modified version of MK system is basically the SI system. I hope this is very, very clear. All right, moving ahead. In SI system, like I said, there are more than three fundamental quantities which were then clubbed together and universally accepted as fundamental. So there are seven base units. There are seven base units. What are those base units? Let's talk about it first and then let's go ahead. Mass is there, length is there, time is there. Standard. Length is measured in meters, that is M. Mass is measured in kilogram, that is K. Time is measured in seconds, so that is S. So the first part was obviously your MKS system. Additionally, you have added four things into it. You have added four things into it: current, temperature, amount, and light intensity or luminous intensity. Current is measured in ampere. Ampere's symbol is A. 5 ampere current, 10 ampere current. That is that ampere, how much current flows through a wire. Thermodynamic temperature or just temperature. It is not measured in Celsius or Fahrenheit. It is measured in Kelvin. Kelvin is the absolute scale. You will learn about it in chemistry. But remember that Kelvin is the scientific unit for measuring temperature. Although Celsius and Fahrenheit is correct, nothing wrong in it, but as a standard. Okay, this is something which you should know. And you should also know that 0 Kelvin, which is the lowest Kelvin possible, is negative 273 degrees Celsius. Okay, or 0 degree Celsius is 273 Kelvin. So the difference is of 273. Amount of a substance, which is mole. 1 mole has 6.02 into 10 to the power 23 number of atoms, number of things. So that is a mole. Short form abbreviation is MOL. Okay, you will learn that in mole concept or basics of chemistry. Luminous intensity is measured in candela, which is CD. How intense is that light? So that light property of how intense it is measured in candela. Okay, so these are the seven base or fundamental quantities and their respective units. Everybody should memorize this. What are those quantities? What are those units? And what are their symbols or abbreviations? Till this point, everybody clear? Cool? Yes? Awesome. Understanding till this point? These are a part of SI system. Please mind it. This is a part of your SI system of unit. Now, later on, they added two more quantities into this particular table of seven quantities. They added two more quantities. They were called as auxiliary units or auxiliary quantities. And those two more units, like you can see right over here, there are two more units that are defined. One is the plane angle and the other one is basically the solid angle. Plane angle, everybody knows. This is 90 degrees, sir. This is 90 degrees and this is basically 180 degrees. Shreyas Sir is dancing like Kathak dancer or something. So guys, this is 90 degrees. This is 30 degrees maybe. This is 45. This is 60. Everybody knows plane angle. measured in degrees, but actually the proper mathematical scientific way of measuring the angle is radian, and you should know that if you have pi radians, it is nothing but 180 degrees. This is something which you learn in basic maths. I have conducted a special class for it on YouTube only. You can check out special lecture for trigonometry. Pi radians is 180 degrees. 90 degrees becomes pi by 2 radians. 360 degrees, one complete revolution, becomes 2 pi radians. So degrees is that additional unit which is measured in, sorry, angle, which is that additional unit, is measured in radians. Okay, is measured in basically radians. So angle, that extra unit, is measured in radians. Okay, this is that extra additional quantity which you have. And then you have the solid angle. This was actually also called as the plane angle or just the angle. Then you have the solid angle. This is angle in 3 dimensions. You don't have to go more into it, depth into it, but just remember an angle in 3 dimension. Usually if you have an arc, this particular measures the angle of the subtended by that arc. If you have an area, if you have a surface area, that surface area won't subtend a 2D angle, it will subtend a 3-dimensional angle. So that 3-dimensional angle is called as solid angle. The 3-dimensional angle is basically called as the solid angle. It is measured in stadian. It is basically measured in stadian. That is what will be also mentioned over here. Yes, steradian. You can see that. This is in radian, this is in steradian. Now, just like we have studied that the length of an arc is a radius times of angle, the plane angle, same way the area over here, which you see, is radius square times the solid angle. This is your plane angle, this is your plane angle, this is your solid angle, and solid angle, this has r square. This has basically square of the radius. That is something which you should keep in mind. Nobody will ask you the formula, but just giving it just in case they give you a question on this, because it is there in NCERT, so you should know. Nothing more specific will be asked, but yeah, you should know the general formula. Length of an arc is radius times the angle. Standard formula. Area of this particular part will be radius square, radius into square, right, into the solid angle which is subtended over here. The solid angle which is subtended over here. This area is this particular area. Okay, this particular area is what we are talking about. So this is basically A, and what is subtended over here is basically your sigma. Okay, you can call it sigma or whatever symbol you want to use. Till this point, is everything clear, my dear warriors? Let me know quickly in the chat box. Right? Till now, what have we studied? We have studied that there are two kinds of quantities, physical quantities, which can be measured in terms of number and unit, fundamental and derived. Derived depends on the fundamental. And because there are units, there are many system of units. One is CGS, one is FPS, one is MKS, depending on which geographical part you are referring to. Different people use different systems for historical reasons, but then we widely use MK system, which is actually modified as SI system. So the SI system has 7 fundamental quantities given as length, mass, time, current, temperature, amount, and light or luminous intensity. There are 2 more auxiliary units, angle and solid angle. Angle is measured in radian and solid angle is measured in steradian. Okay, solid angle is measured in steradian. Perfect. I hope till this point everything is absolutely clear and you're noting it down. Yes, note it down, mark it in your NCERT. That will be very, very helpful. Now there are more units. There is one table given in your NCERT. You can open it up. I hope you are keeping your NCERT side by side or at least on a separate tab, so that as we are talking, we can simultaneously highlight or mark on the NCERT. All right, so keep doing that. So you'll see a particular table, not very important, but few things you should know, like how many seconds make a minute. Everybody knows 60 seconds make a minute. how many minutes make an hour or how many seconds make an hour. 1 minute is 60 seconds, 60 minutes make an hour, so 3600 seconds make an hour. One day is 24 such hours, so you multiply by 24, 3600, you will get 86,400. This number is very important, useful, especially where calculations involve the day and you have to convert it into seconds. Then year, not so important. Degree radian conversion, everybody knows pi radian is 180 degrees. Liter is 10 to the power minus 3 meter cube. You should know this. So which all important things are there? I will mark it over here. See, this is everybody knows. This also everybody knows. This is not so important. This you learn it in trigonometry anyways. 1 liter is 10 to the power minus 3 meter cube, will be useful, especially in fluid mechanics. 1 ton is 1000 kg, very rarely used, but it's okay if you know it. Carat is 200 mg, very rarely used. It's okay if you know it also. Bar, you will learn it in chemistry as well as in fluid mechanics. 1 bar is 10 to the power 5 Pascal. You should know it. 1 Curie is 3.7 into 10 to the power 10 per second. Now, radioactivity has been deleted. Law of radioactivity, so not so important. Wrong 10 also deleted because radioactivity decay is no longer a part of the syllabus. Quintal is 100 kg. Barn is basically 10 to the power minus 28 meters square. All right, these are areas basically. Air, hectare. Now these things are not so important. Atmospheric pressure is 1.01 into 10 to the power 5. Again, this becomes important. So these are the only important things which you should know. Apart from that, everything else is pretty much standard. Even if they give you carrot in the exam, well, not that carrot to eat, that carrot where you measure gold, 24 karat gold, 20 karat gold, 20 karat diamond, that is that carrot over here. Okay, so 200 milligrams. Okay, that conversion factor they will give you, but in case you want to remember it, no harm in remembering this ton and a carat. Okay, apart from that, the remaining things not necessary. All right, moving ahead to the next part where we talk about basically significant figures. I hope you're enjoying the class and you're smashing that like button down there. Yep, do that. Mark your attendance quickly. Good evening, my dear warriors. Nice to see all of you. Those of you are joining in a little bit late, you can rewind back and catch up or continue with the live class, and whatever part you missed, you can watch it later on. Okay, cool. So, significant figures. See, this chapter entirely deals with units, dimensions, errors, how you represent physical quantities, etc. So when you write a number, say my height is 7.2 feet or the length of this is 2.765 meters. So you're using certain digits, and certain digits might be of importance, might not be of importance. So depending on how many digits make a difference, how many digits are particularly of importance and some digits may not matter at all, you define the term called as significant figures. Like writing 07 is same as writing 7. Writing 7.62 or 76.2 into 10 to the power minus 1. I have not changed much of the values. This power of 10 did not really affect the value of this number nor its accuracy. So you will see over here 0 was insignificant, and here also this power of 10 did not change the value. I mean, I just shifted the decimal place, that's all. So this power of 10 also is pretty insignificant. So there are certain rules to know how many significant digits are there and how many significant figures are there in a particular number. This rules is what we are going to see. The rules what are there to calculate the significant figures is mentioned in this particular paragraph. As we discussed, every measurement involves errors. So there is no measurement without any error. Like even there is a biggest of the biggest teacher, they will also make a mistake. Students make mistakes, you get negative marks in the NEET exam, right? So even measurements have errors, and that is accepted, that is understood, but we have to deal with it. If you know how to deal with it, that's it, you will conquer it. So the result of the measurement should be reported in a way that indicates the precision of a measurement. Normally, the result which is reported is a number that includes all the digits in the number that are known reliably plus the first digit that is uncertain. The reliable digits plus the first uncertain digits are known as basically the significant digits or significant figures. So, you know, you will, whenever you will write a measured value, let's say for example, the length is 7.93, you always include the reliable ones, 7.9 for sure. This 3 might be, little bit dicey. Maybe it has just become 3. Maybe it was 7.29. Maybe it was 7.29. It has been rounded off to 7.93. 7.929, maybe it was rounded off to 7.93. So this digit is that uncertain digit. Rest all digits are basically reliable. So total number of significant figures in this is 3, 1, 2 and 3. That is what is counted as the significant figures. That is what this particular line tells. Understood, guys? So usually that last decimal might have come by some internal process, by rounding it off or by coming closest to that particular number. That is why usually it is called as the uncertain digit, but we still consider it as our significant figure. Okay, or else there is no end to it. There will be somebody at the end, right? So that last person is always that unreliable one. Okay. Now, they have given the same kind of examples, the length of an object or the time taken, etc. For example, the length of an object is 287.5, has 4 significant figures. The numbers 2, 8, 7 and 5. All these 4 digits are, important for us, but out of them, 2, 8 and 7 are certain, while the digit number 5, which is the last one, is the uncertain. So, whenever you report this kind of a result, it includes more digits than the significant digits in a superfluous and also misleading, since it would give a wrong idea about the precision of a measurement. See, what they are saying is, if somebody writes 287.5, let's say 00, okay? Now, if you write those extra zeros, means you are certain till this point, versus over here 287.5, you are only certain till that fifth digit or digit number 5. So when you add extra numbers, even though it is 0, it can be misleading. Even though mathematically they are equal, this number 287.5 and 287.5000, mathematically they are equal, but because you added that extra 0, maybe you are so sure till that decimal point. So it can affect the precision, the accuracy of the reported measurement. So you should be careful when you are putting these zeros, and that's why you will see most of the rules for finding significant figures have rules involving about the placement of those zeros, because the placement of that zero matters a lot. So those rules is what we are going to see now. The significant figures, as expressed before, express the precision of the measurement, which depends on the least count of the measuring instrument. So how accurately you are able to measure this? How are you able to measure 287.5? Maybe 0.562, maybe 0.561. That depends on something called as the least count of an instrument. For example, the least count of your normal watch is 1 second. No matter what you do, you can't measure beyond 1 second. You can measure an hour. Hour is bigger than a second, but you can't measure 0.001 second, because the smallest measurement possible in a watch is 1 second. Same way, in your meter scale, normal scale which you use, you can't measure more than 1 millimeter accuracy. You can't measure 0.001 millimeter. No, not possible, because the divisions are only that big. You can measure kilometers, but you can't measure 0.1 millimeter, 0.05 millimeter, because it is lesser than the smallest division on that scale. So that smallest division on the scale is basically called as the least count. And that decides how accurately, how precise were you able to make this particular measurement. Now the choice of change of different units does not basically affect the number, does not change the number of significant digits or the figures in the measurement. This is very, very important line. The choice or the change of different units do not change the significant figures. This important remark makes most of the following observations clear. So they have given examples for that. Say the length is 2.308, it is measured in centimeters. Let's say instead of centimeters, you go to meters. So what will happen? This will become 0.0 because you'll shift the decimal two places, centimeters to meters. So it will become more smaller in number, 0.02308 meters. And you can also measure it in millimeters. So centimeter to millimeter conversion means you will shift the decimal this place. So it will become 23.08 millimeters. Or you can also measure it in micrometers, 23080 micrometers. Even if I write it like this or like this, do not think the significant digits have changed, because you might say, sir, in centimeters, 1, 2, 3, 4, 4 digits were there, sir. In meters, 1, 2, 3, 4, 5, 6, 6 were there, sir. In millimeters, 1, 2, 3, 4 are there, sir. No, no, no. All of them have same number of significant figures. So I know you might be thinking, sir, this 0 and this 0 is not important, sir. Yes, they are not important. How did you know, sir, they are not important? Just because you knew the centimeter value? No. In fact, there are rules which we are going to talk about. So there are rules in determining which zeros are important, which zeros are not important. And you should know that by just changing the unit, it does not mean you have changed the significant figures. You have to make sure when you convert, final significant figures is equal to the initial significant figures. So this also implies that the location of the decimal point has no importance in determining the number of significant figures. Like you saw over here, where the decimal place went does not affect. So never ever worry so much about the decimal place. Place might go from here to here, doesn't matter much. Significant figures will not change. So what are the rules? Here are the rules. All the non-zero digits are significant. All the zeros between two non-zero digits are significant no matter where the decimal point is, if at all. So let me explain the first two rules first. See guys, example 68 has how many? Two significant digits. All non-zero digits are significant. But if there is a zero between two non-zeros, that is also significant. For example, if I have the number 708, this zero is between two non-zeros, so it has three significant figures. If I have the number 100205, these two zeros and this zero is between three non-zeros, so 1, 2, 3, 4, 5, 6. So it has six significant figures. That's all it is saying. Even if there is a decimal point, if it is like 20.501, 1, 2, 3, 4, 5. This has five significant figures. Even if it is like 7.803, this has 1, 2, 3, 4, four significant figures. So decimal places do not play important role here, and number of zeros in between two non-zero digits always to be counted as significant. That is the first 2 points. Next point. If the number is less than 1, the zeros on the right of the decimal point but to the left of the first non-zero digit are not significant. The underlined zeros are not significant. Okay, so this rule is done. All non-zeros are non-significant. All the zeros between two non-zeros are significant. This is done. Now what is this? If the number is less than 1, the zeros to the right of the decimal but to the left of the first non-zero are not significant. They are not significant. Best examples of this. Say for example 0.058. This number is less than 1. Everybody agrees? So all these zeros become insignificant. Only two significant digits. As simple as that. Similarly, 0.000201. These zeros to the left of the non-zero, never ever significant. This and this zero is between two non-zero numbers, so hence significant. So three significant digits. That is what this example says. Clear? Very straightforward. The terminal or the trailing zeros in a number without a decimal point are not significant. Okay. Thus 123, which is 123 0 centimeter, 123,000 millimeters has three significant figures, the trailing zeros being not significant. However, you can also see the next observation. The trailing zeros in a number with a decimal point are significant. Number fourth, 1, 2, 3, 4, 5, fifth point. And there can be also some confusion in the trailing zeros. Suppose the length is reported to be 4.70. The reason why I'm reading all this is because all these three rules are related to each other and important. It is evident the zeros here are meant to convey the precision of the measurement and therefore are significant. If these were not, it would be superfluous to write them explicitly, meaning it will be unnecessary. Superfluous means it is unnecessarily you are giving too many things. The reported measurement would have been simply 4.7 meters. Now suppose we change the units, okay, this to this to this. Since the last number has trailing zeros in a number with no decimal, we would conclude that there will be some error from the observation that the number of two significant figures, while in that fact that four significant figures and mere change of unit cannot change the number. So let me explain this to you. First of all, if you talk about this over here, terminal or trailing zeros in a number without a decimal point are not significant, very, very important. Like for example, 700, these are not important. This is important. Or 90900, this and this are important, these two are not important. Or let's say for example, 805, 8050 point, or maybe just 00 over here. This is significant, this is significant, these two are not significant. That is what it says. Trailing means ending zeros, okay, without a decimal point. This is very important. Without a decimal point, they are not significant. But the moment there is a decimal point, then the trailing zeros automatically become significant. For example, if this was 7.00, this and this automatically become important. Even if it was 70.0, this automatically becomes important after the decimal. So this 0 also becomes important. Same way, if I put it as 80.500, this and this is between two non-zeros is obviously important, but these two zeros are after the decimal, so they become important. Same way, even over here, if I write 9090.0, these two are definitely significant. This is between two non-zeros. This zero is after the decimal, so significant, and between any two significant, this also becomes significant. So automatically the number of significant digits increase the moment you put a decimal place. Okay, that means you are sure of the accuracy till that level. See, understand, when I just write the number 7 versus 7.00, that's what they have mentioned over here in this particular paragraph regarding the trailing zeros. That confusion, what they are talking about is, what's the difference between 7 and 7.0 and 7.00? See, the meaning of putting extra zeros means that I'm so sure of the measurement till that decimal. So, although numerically they are equal, but understand this is more accurate, more precise, whereas this is less accurate. More error is there in this because I have gone till the second decimal to give the perfect value. This is just 7, maybe it was 6.99, but here I'm sure it is definitely not 6.99, it might be 7.001. In the third decimal there might be an error, but till the second decimal I'm sure. So that is the meaning of putting that extra zeros, and that is the place where most of the students have that confusion. Sir, isn't the number equal actually? Yeah, the numeric value is the same, but physics wise, scientifically, the meaning is different. Okay, understood the difference till this point? Clear? Awesome. Now, in that last point where they are basically converting it, now since the last number has some trailing zeros in a number with no decimal, we would conclude erroneous from observation 1 about that the number has only two significant figures, while in fact it has four significant figures and a mere change of units cannot change the number of significant figures. See, take this example. Okay, here, because this number is less than 1, obviously this 0, this 0, this 0 are not significant, this 4 and this 7 are significant. A lot of people think that these two zeros are not significant because this is a number less than 1. No. If there are zeros after a decimal place, like you can see over here, a number ending with zeros after a decimal, they are significant. So these two zeros are also significant figures. So this has actually significant figures. So the last two decimal places here also become important, okay, because these zeros are after a decimal. So we are just using this particular rule, nothing more, nothing less. So even if you convert this kilometers into millimeters, make sure that you are putting those two zeros. You are putting those two zeros. But you might think, oh, wait a minute, sir. This has only two significant figures. This has only two significant figures because there is no decimal and all of that. No, this number has four significant figures even after the conversion. Even after the conversion. But then you will be like, sir, but as per the rules, this particular rule, ending zeros without decimal should not be considered as significant. Getting my point? Here, this number had four significant figures, but when you convert it into millimeters, what happened? It became 4700. 4700. Those two zeros, as per this particular rule, are not significant. So then you might think, so this does not have four significant figures, but only two significant figures. So there comes that confusion. So to avoid that confusion, what happens is, the best way to report every measurement is in scientific notation. The best way to represent any measurement is in scientific notation. Very, very important. And what is scientific notation? It is basically in powers of 10. In basically powers of 10. So you can use positive powers or negative powers, it doesn't matter. So now this particular millimeters issue which was there, what you do, you write it as 4.700 into 10 to the power 3 millimeters. Now the moment you write it like that, what happens? Because these two zeros are after the decimal, automatically they get counted. Automatically they get counted as significant figures. So one will be 100% sure it has four significant figures. This is called as scientific notation, where you express it as powers of 10. Express it as powers of 10. 10 raised to 3, 10 raised to 2, 10 raised to 7, 10 raised to minus 6, 10 raised to minus 9, etc. etc. Remember one thing, that the power of 10 is irrelevant to the measurement. The power of 10 is irrelevant to the measurement in terms of significant figures. So significant figures do not get affected by the powers of 10. Okay, I hope this is absolutely clear. Understood this particular example which they gave, guys? So what an amazing set of rules that we have. Okay, so probably we can just take some examples over here at this point of time. Say for example, I told 0.027050 into 10 to the power say 6. How many significant figures it has? What you will do? You will think, oh, this number, whatever this is less than 1. So these zeros should not be counted. Powers of 10 not to be counted. What should you count? All the non-zeros. Any zero between two non-zeros counted. Now this zero you might think, oh wait a minute, it is towards the end. But think again, it is after the decimal. The moment it is after the decimal should be counted. So 1, 2, 3, 4, 5. So it has 5 significant figures. Understood how to do the calculation? Clear? Same way, for example, if I have the number, you know, say for example, 2900, 2900, this has only two significant figures. This has exactly two significant figures. But if I write it probably something like this, 2.900 into 10 to the power 3. Although numerically they are equal, or I can just put 10 to the power 2, sorry, 10 to the power 2. Yeah, I'll shift, my bad, sorry, 10 to the power 3 only. What did I just do? Yeah, numerically they are equal, Okay, I'm just shifting the decimal 3 places, but this has different amount of significant figures. First of all, 10 to the power 3 is never counted. Remember that. Just like these zeros were never counted. But what will be counted here is this 2, this 9, and these zeros are after the decimal, hence they will be counted. So this one has 2 significant figures. This one has 4 significant figures. This is actually the scientific notation, if you realize. Scientific notation is where? Scientific notation is where you write it in a some number into 10 raised to something. 10 raised to something. Okay. Till this point, everybody clear? All right. Now there is a table which is given behind, which is basically different powers of 10 and their prefixes and what they are called. You should know it actually, but it is very simple to remember. It's not that difficult. See, if it is 10 to the power 3, it is basically called kilo. If it is 10 to the power 6, it is called mega. If it is 10 to the power 9, it is called tera. Kilobyte, megabyte, terabyte. Sorry, this is giga. 10 to the power 12 is tera. So if you have played with hard, or you know what the hard disk size is or the RAM size of a computer is, you would obviously be aware of these terms: kilobyte, megabyte, gigabyte, terabyte. So that is how it goes. K is for 10 to the power 3, M is for 10 to the power 6, G is for 10 to the power 9, T is for 10 to the power 12. The reverse also holds true for negative powers. 10 to the power minus 3 is milli. So use small symbols for big powers. For positive powers, you use capital symbols. For negative powers, you use small small alphabets. 10 to the power minus 6 is micro. 10 to the power minus 9 is basically nano. 10 to the power minus 12 is basically pico. And 10 to the power minus 15, you will be using it in nuclear physics. That is basically Fermi or femto. So these are the powers of 10 which you should know by heart, and you will be using it very, very frequently. You'll be using it very, very frequently. Like for example, over here, I can definitely write this as 2.900 kilo. If this was, I don't know, it could be anything. It could be anything. Maybe this was Newton. So this would be also Newton. This would be kilonewton. If this was joules, this would be joules, this will be kilojoules. So that is the prefix of the powers of 10 which you use in many examples. This is basically your scientific notation. Is this point clear till this point? Absolutely. Awesome. Awesome. Now, the last thing over here in significant figures is where a scientific notation is ideal for reporting a measurement, but if this is not adopted, we use another set of rules for a number greater than 1. See, not every time you will see scientific notation applicable. Very, very important what they are saying. If scientific notation is ideal, fine. There are a lot of things ideal. Like ideally, we should have started studies then. We should have prepared this much by now. By now, we should have cleared this. By now, we should have got all India rank this. All things are ideal, but realistically speaking, if this is not adopted, very, very important, we use the rules as follows. For a number which is more than 1, for a number which is more than 1, without any decimal, the trailing zeros are not significant. As simple as that. Number more than 1, the ending zeros are not significant. For a number with a decimal, the trailing zeros are significant. The digit 0 conventionally put on the left of a decimal of a number less than 1, like 0.1250, is never significant. However, the zeros at the end of such number are significant in the measurement. So they say if you're not using scientific notation, simple rule guys, a number is more than 1 without any decimal place, okay, no decimal place, you should not even count them. For example, check this out. For a number greater than 1, okay, say for example 2900, obviously you will not count them. This is definitely counted. All right, same thing. If a number with a decimal, the trailing zeros become significant, meaning if you have something like 29.00, These zeros are after the decimal, so they have to be counted. Or 290.0, the ending zeros will be counted because there is a decimal place. As simple as that. That is what this particular rule mentions when you are not using scientific notation. Now, the last rule is multiplying or dividing factors which are neither rounded numbers nor numbers representing measured values are exact. They have infinite number of significant digits. Exact, and they have infinite significant digits. These dividing factors, multiplying, they are neither rounded or they are exact numbers like constants. For example, the value of pi, value of e, these are constants which have infinite, or you can take as many significant numbers as you want. Say for example, I'm finding the diameter, and diameter is the radius multiplied by 2. So the radius might be 5.3 centimeters. When I multiplied by the 2 number, how many significant numbers does 2 have? 2 has infinite because it's an exact number. So I can put as many decimal zeros as I please. So there is no end to it. So there is no end to it. Understood this point, everyone? Clear? Okay. So constants like pi, when I say circumference is 2 pi r, how many significant figures 2 has? Infinite. Pi, infinite. R will be limited because a radius will be measured. Okay. So understand this. So constants, physical constants, which are pure numbers, or just multiplying factors or dividing factors, they have infinite or as many number of significant figures as you please. Keep that in mind. Now, till here, we have figured out how to calculate the number of significant figures, be it any particular number, any number. So now you know whatever number I give you, you will be able to tell me the significant figures. Let's say I give you a number like 0.1205. Immediately you will be like, sir, this 0 is not important. This is a number less than 1. This, and this are important. Perfect. If I tell you it is 50.200, you'll think, okay, this is important, this 0 is between these two, important. These zeros are ending zeros after the decimal, hence they are important. If I tell you a number like 7008001000, you will think, okay, this and this are important, this is also important, these two and these two are between two non-zeros, these two are not important. So now at the back of your mind, you don't have to sit and by heart all these rules. It is pretty much logical which zeros are important, which zeros are not important. Okay, so please go through this particular explanation again and again. Let it become more natural rather than remembering these rules, because nobody in the NEET exam is going to ask statement, significant figures, which are the zeros which are important. No, that kind of question will not come. Rather, they might give you a question, find the number of significant figures in the following. Okay. All right. Next, whenever you play with significant figures, maybe you're dividing, multiplying, adding, etc., how do you tackle the final result? How many decimals will you put? That is a very important question. So, whenever, this is a very important rule again, whenever you are multiplying or dividing, the final result should retain as many significant figures as there are in the original number with the least significant figures. Very, very crucial. Look at this. Density is mass by volume. The numerator has 1, 2, 3, 4. 4 significant figures. The denominator has 1, 2, 3. 3 figures. Now the final result, if it is recurring or has many decimal places, you cannot write those many decimal places. 4 and 3, 3 is the least. So the least significant figures is 3. Final result will be rounded off to 3 significant figures. Got it? Very simple. Similarly, speed of light is given something, etc. Okay. three significant figures and 1 year is this much. Okay, so here what they are saying is, if needed, wherever, for example, speed of light, if you measure it accurately, it becomes, you know, uh, goes to many decimal places, 2.998 and all that. But you might not need it so much, so you will round it off to generally two or three significant figures. So if you round it off to three significant figures, you will get 3.00 into 10 to the power 8 meters per second. So that's how you would represent it had it been needed somewhere over here. Okay, so generally, when there are too many significant figures, you might not need all those significant figures in the result. So you will generally truncate many significant figures and you will use up to generally two decimal places. Even in NEET, even in JEE, you would have seen this. The answers which are asked are up to two decimal places. Okay, not beyond that. Okay, that is what is generally expected. Okay, so now similarly, say for example, if you multiply two numbers, let's say for example, 2.000 multiplied by, let's say, 4.00. If you multiply it numerically, 2 fours are 8. Now this has 1, 2, 3, 4, four significant figures. This has 1, 2, 3, three significant figures. So final answer should also have three significant figures. Hence it will be nothing but 8.00, 1, 2, 3. Exactly. So whether it is multiplication or division, always use the least significant figures which is used in the division or in the multiplication. Fair enough? Clear? What about addition and subtraction? What about addition and subtraction? For addition or subtraction, the final result should contain as many decimal places are there in the number with the least decimal places, not significant figures. Now you go to decimal, not significant figures. There's a difference. For example, 7.000 plus 2.0. You just check the decimal places. This has 1, 2, 3. This has 1. This has 1, 2, 3. This has 1. So when you add them, final answer should contain exactly one decimal place. So for addition subtraction, it is decimal places. For multiplication division, it is significant figures, the least of them. That's the major difference. Another example that they have given, if you add this number and this number, by normal addition, if you do it on the calculator, you will get it as 663.821. But you can see there are many decimal places over here. There is one number with only one decimal place, another number with 2, another number with 3. So what will you do? You will finally write it as one single decimal place. So you will round it off and you will finally write it off to 663.8 grams, because that is the correct way of writing it. Single decimal place, because that is the least of all the three. Same way they have done it for subtraction also. 0.307 minus 0.304 is 0.003. Now you might think, sir, I have gone till third decimal place. Okay, till third decimal place over here. Yes, that is what you are going to do, because there were three decimal places here. There are also three decimal places over here. All right, I hope this is absolutely very, very clear. Now, in the last part of that note, we should not use the rule 1 applicable for multiplication and division and write 664 as the result in the example of addition and subtraction, and 3.00 into 10 in the result of subtraction. They do not convey the precision of the measurement properly. For addition and subtraction, the rule is in terms of decimal place. They are just telling, even if you write this number as 3 into 10 to the power minus 3, okay, it is fine. There is no need of writing 3.00 into 10 to the power minus 3, because for addition subtraction, significant figures is not what you worry about. You worry about the decimal places. So if you write the final answer over here as maybe 3 into some power of 10, the number of decimal places will get affected. The number of decimal places will get affected. Plus, it will not convey the importance of this particular rule. This rule talks about decimal places. So don't worry about significant figures for addition subtraction. Vice versa, for multiplication, division, do not worry about decimal places, worry about significant figures. That's all they are saying. While writing, they sometimes try to confuse students. Now, Sometimes you might be worried, sir, how do I round off things? It's very simple, guys. So they are given three different cases. They are given three different cases whenever you have to round off. Always check the last digit, and based on the last digit, the previous digit will be either added by 1 or will be kept as it is. And this confusion always happens. How do I round off numbers? So the rule by convention is that if the preceding digit is raised by 1, if the insignificant digit is to be dropped, the underlined digit in this case is more than 5 and is left unchanged if it is less than 5. The preceding digit is raised by 1 if the previous insignificant digit to be dropped uh, is more than 5 and is left unchanged if the later is less than 5. What does it mean? It means if I have the number 24.68, I want to get rid of this. Check the previous digit. Is this 6 more than 5? Yes, this 6 is more than 5. So what you do is you add basically 1 to it. So it will basically become 24 point. Instead of 6, add 1, it will become 7. So you increase the previous digit by 1 if it is less than, sorry, my bad. I did the wrong way. If it was 24.68, check this number 8. Yes, it is more than 5. So this one, you increase it by 1. So it will become 24.7. So the previous digit is raised by 1 if the last digit is more than 5. Another example, if it is, let's say, 67.9, or let's say, for example, 63.9. This last digit is more than 5. So this one will be incremented by 1. So it will be basically 64. That's what this rule says. Now, if it is less than 5, then you leave it unchanged. For example, if it was 24.63, this 3 is less than 5. So leave it as it is. So it will become 24.6. Same way over here, if it was 63.4, this number 4 is less than 5. So keep this digit 3 as it is. So rounded off number will be 63. That is what this rule says. Till this point, everybody clear? Okay. Now, the last case will be, what if the digit is exactly equal to 5? What if the last digit is exactly equal to 5? If the preceding digit is even, then the insignificant digit is simply dropped, and if it is odd, the preceding digit is raised by 1. So the way they write it looks very confusing. What they mean is that, for example, if it was 24.5, check the previous digit. What is it? It is even, right? So when it is even, then keep it as it is. Just drop that previous digit. It's okay. And just write it as 24. If it is even, keep it as it is. Even should not be affected. But take this example. Imagine if it is 63.5. The last digit being equal to 5. The previous digit you should check. Oh, it is odd. So if it is odd, increase it by 1. You add 1 to it. So hence it will become 64. So if it is odd, make it even. If it is even, keep it even. Odd means odd man out, no? So remove it, make it even. So even is what we like. Is this clear, my dear warriors? All right. Awesome, awesome, awesome. Now, I think this part I have already mentioned right over here also, like speed of light and everything, and even that part where we talked about constants. Remember, constants have infinite number of significant figures, right? So you can choose as many significant figures as you want, which you feel is appropriate for your calculation. But you generally, when you have to round it off to some particular thing, then what you do is you take one extra digit before rounding it off. Okay, you take one extra digit. I'll give an example. Imagine, just for example, some constant was, it had many decimal places. It was 6.9378 etc. And we were just bothered about two decimal places. So without looking at any other decimal place, you just took these three digits. Then that particular Pandu will write the constant's approximate value as 6.93. But that is not correct. This is wrong. This is not 6.93. Because after 3 there is 7. So had you rounded it off properly, because this 7 because this 7 is more than 5, actually you should increment this by 1. So the correct rounded off value should have been 6.94. Understand that. So whenever you want to truncate the number of decimal places of a large significant figure like pi, e, constants basically, then till whatever decimal places you want to write it down, add one extra or keep one extra decimal, then round it off and then write the value. That is more accurate. That's what they are saying. Is that clear? Absolutely. So for writing the value of pi till 2 decimal places, go till the third decimal place. Okay, 142. 2 is lesser than 5. So what will you do? Keep the number 4 as it is. So hence it is 3.14. That's what it says. All right. So then there are two examples. Okay, in the in-text questions, we'll just go through it, what they are. First one is where there is a cube whose side is to be measured as 7.203. What is the surface area and the volume? Now, when you talk about the surface area of a cube, realize one thing, there are basically 6 sides and each side has an area of a square. So multiply by 6. So 6 times of side square will be the answer for the surface area. Now, when you find the numeric value using a calculator or take your time and calculate it, you will get many decimal places, many significant figures. But remember the rules. You cannot put so many significant figures because you are multiplying side with another side into 6. Multiplication, what do? Check the significant figures. This number has 1, 2, 3, 4. 4 significant figures. So the final answer should also have 4 significant figures. So out of this big number, get rid of many of the digits like 2.2999. This number 9 is more than 5. So it will be rounded off to 3. So 2 will become 3. 2 will incremented by 1. So 311.3. So 4 significant figures. Understood how we have wrote down the answer? Although this seems very real, this should be the correct answer, but no, the initial side only was measured till the fourth significant figure. So the final answer can't contain more significant figures than the actual measured value. Same thing over here. Volume is the volume of this cube will be side raised to 3. So side into side into side. Again, multiplication. So when you multiply 7.203 into 7.203 into 7.203, you get this as the answer with many significant digits. But since this had 4 significant digits, you will round it off to 4 significant figures. You can see the number 1 is less than 5. Hence, what you have done, you have kept the previous digit as it is. Cool? That is how rounding off works. Another example where mass is given and volume is given, express the density. Density is mass by volume. Mass is 5.74, volume is 1.2. When you divide these two numbers, check the numerator has 3 significant digits, 1, 2, 3. The numerator has 2. So the final answer, even if there are more digits which come while calculating it, you will put it only till 2 significant digits because this is division. Is that clear? Everybody understood till this point? Awesome. So till now, what have we done? We have seen units, we have seen the fundamental and derived quantities, the 7 fundamental quantities and the 2 auxiliary units. We have seen, what is the meaning of significant figures and how the placement of decimals, zeros, everything matters. We have learnt about the powers of 10 being insignificant and the scientific notation, all the exceptions, rules of significant figures, and how do you add and multiply and preserve the digits of significance or decimal places. That's what we have learned till now, right? Shall we continue? Awesome. Now, the next is for errors. Like I mentioned some time back, whatever you do in life, there will always be some error. There will always be some uncertainty in the measurement. Now, how much uncertainty is there in that measurement is basically the error in that measurement, right? And say for example, say you measure the length of something, and the length of something is measured to be uh, you know 16.2 centimeters. When you say it is 16.2 centimeters, remember that last digit is always that tricky digit, because it would have come after rounding it off, or because that scale marker was very close to that object's edge. That's why you just said, okay, it is 16.2. So that uncertain digit is always there. So that's why it is 16.2, and there is a decimal point 1 centimeter of uncertainty in it, hence plus minus zero point 0.1 centimeters. This is your absolute error. This is your absolute error, and this is your most likely value. Most likely value. Most likely it is 16.2, but I'm not very sure. We have to give it some doubt, benefit of the doubt. It could be 16.3 also. It could be 16.1 also. So that is what it means. Same way, when I write 10.1 centimeters, that last single digit is slightly uncertain. So it could be 10.1 plus minus 0.1 centimeters. So everything that you measure around you has some uncertainty. So if I tell you, my dear warriors, that listen, the time that I measured using a very special clock was 6.23 seconds. This is always that uncertain digit. So actually what I mean is 6.23 plus minus point till the second decimal. So the third digit is the problem. So 0.01 plus or minus seconds. So it can be either 6.22 or it could be either 6.24. Somewhere in between that is where the measurement lies. This is your absolute error. So this is your absolute error. So plus minus delta t, and this is the most likely value. Most likely value. So length will also be L plus minus delta L. Mass will be M plus minus delta M. Force will be F plus minus delta F. Delta stands for that uncertainty. F stands for that most probable value in that case. Okay. Till this point, everybody clear? Now, if everything has error, all those things which depend on these quantities will also have error. Imagine somebody was measuring the area of a sheet. They measure length to be this. They measure the area to be, sorry, breadth to be this. You can again see this has some error here. This was the most likely value. So the final area will also have certain amount of error in it. Yes, the final answer of the area will also have some centimeter square of area in it. So how to calculate that uncertainty when another quantity depends on more quantities which have error in it? The answer to that is with some rules. So what are those rules? Very simple. If the quantities are being, like you can see, combining the data will be valid to the significant figures. However, if data are subtracted, okay. If a set of experimental data is specified to n significant figures, a result obtained by combining the data will also be valid to n significant figures. However, if the data are subtracted, the number of significant figures can be reduced. Number of significant figures can be reduced. For example, okay, see guys, 12.9 minus 7.06. Both are given till 3 significant figures. Both are given till 3 significant figures. Like you can see 1, 2, 3, 1, 2, 3. When you subtract them, you will notice that the final answer may not be up to 3 significant figures, but maybe 2 significant figures, like you can see over here. The reason for that probably is mentioned over here. As uncertainties in subtraction or addition combine in a different fashion, the smallest number of decimal place rather than the number of significant figures. If you remember, when we spoke about how to add and subtract and how to tackle with those decimal places, only for addition and subtraction, remember you have to always count for the number of decimal places. You have to always count for the number of decimal places. This had one decimal place, this had two decimal places. So the final answer should also have exactly one decimal place. So you cannot put two decimal places here. That is why you will round it off. You have basically round it off to the least decimal place, to the least decimal place. Hence, the moment you rounded it off, it became two significant figures. Very, very interesting. So it is not necessary that your final answer retains as many significant figures as the original result. It might have less, especially in the case of subtraction, something like this, addition also, because the least of the decimal places are always accounted for. Now, whenever you add and subtract, their errors also get added and subtracted. And what happens while multiplying and dividing, that also will come to it. So we'll talk about addition, subtraction, and multiplication, division, etc. So, say for example, uh, you are measuring length 1 to be 2 plus minus zero point 0.1, length number 2 to be 3 plus minus 0.2. Then when I find L1 plus L2, just normally add these two. Just normally add these two. 2 plus 3 is nothing but 5. And just normally add these two. So it will be 0.1 plus 0.2, which is basically 0.3. But if you do L2 minus L1, the subtraction, 3 minus 2, 3 minus 2 is 1. So do the normal subtraction here. But here, don't subtract these two. Always the errors get added. So it will become 0.3 over here. So remember this very important thing. During addition and subtraction, the absolute errors always add. The absolute errors always will add up. They will never ever subtract, whether it is addition or subtraction. Keep that in mind. But during division, multiplication, etc., it's the relative error which matters the most. So the relative error of a value of a number specified to the significant figures depends not only on the n but also on the number itself. Okay, we'll come to that also now. So to explain this particular statement, they have given one example. If you take a number like 1.02 grams, 1.02 grams, because that last digit is uncertain, so I can write it as 1.02 plus minus 0.01 grams. That is probably the error in it. It also has some relative error in it. It also has some relative error. Now, what is the meaning of relative error? Relative error is how much error does it have upon how much original quantity that you are measuring. So this is that error. Divided with this, what you get is the relative error. And you multiply it by 100, it becomes percentage. Okay, there is some 0.01 error in this much. So you multiply by 100, you get how much percent of error is there in that quantity. So when you do that, the relative error in 1.02 is 0.01 divided by 1.02 into 100, which is becoming 1%. Similarly, the relative error in 9.89 is basically 0.01 is that uncertainty divided with 9.89 into 100, it again becomes 0.1%. So with this example, what do you see? The relative error of a value of a number specified to significant figures depends not only on that number but also the number itself. So even if it was expressed till two decimal places, the error was 1%. But if you change the number to 9.89 or some other number, even if it is expressed till two decimal places, still what you found was the relative or that percentage error was completely different. So understand this concept that Just because you have expressed a number till certain decimal places does not mean there is more or less percentage error. It also depends on what that number is. On what that number is. Like you can see over here, both were expressed till two decimal places, but the percentage error in one was 1%, other one was 0.1%. Is that absolutely clear? Everyone? Okay. Now, talking about this particular paragraph where intermediate results in the multi-step problem should be calculated to more significant figures than the number of digits in the least precise measurement, and the rounding of errors can build up. However, if we had written this thing, okay, this example justifies to retain one more extra digit uh, than the number of digits in the intermediate steps for complex multi-step calculation to avoid additional errors. Okay, so I'll tell you what this means. Say for example, when you are doing something like, okay, 2.05 multiplied by 7.03, and then whatever result you get, then maybe you have to divide it with uh, 3.1, then you have to probably add it to something, then you have to probably again multiply it with 5.78. Okay, some multi-step problem is there. So what you might think that, okay, let me follow rules at every place and let me, get it till proper significant figures or, proper decimal places at every step. Don't do that. Whatever accuracy or whatever significant digits are needed in that particular step, add one extra digit just for safety purpose for a multi-step problem, and then keep on doing that addition, multiplication, subtraction, whatever it is till the end, and in the end you put it till the proper significant figures. Why they are saying that? Because if you are omitting certain digits, there might be some small error which will come up. That small error will get accumulated, and every step that error might become more and more and more, and maybe that error might become little bit noticeable towards the end had you not considered those extra digits. It kind of makes sense also, right? When you are say multiplying, multiple numbers, and every time you multiply you round it off, every time you multiply you round it off, rather than you multiply, and in the end you round it off. That makes more sense. That is what this paragraph is saying, which I think most of you will be doing. All right, till this point absolutely clear, my dear warriors? Cool. Great. Now let's talk about the dimensions of physical quantities. But before that, one small thing: whenever you have multiplication division, there is something called as the power rule. I will talk about it. So if you have any physical quantity given as some constant into p1 raised to alpha, p2 raised to beta, etc., then the relative error in that physical quantity is alpha into delta p1 by p1, whatever the mod value, plus beta into delta p2 by p2, and so on and so forth. This is what you do for multiplication, division, etc. This is called as the power rule for relative errors. Let me demonstrate this with an example. Imagine kinetic energy is half mv square. K is like the physical quantity, C constant is half, mass is one of the quantity, and P2 is basically V square. So the relative error in the kinetic energy does not depend on the constant. You take the relative error in the mass, you take the relative error in the velocity. Mass is actually raised to 1, so you multiply it by 1. Velocity is raised to 2, so you multiply it by 2. That's all. That's what it says. Simple. Similarly, the time period of a simple pendulum is 2 pi root of L by G. So the relative error in the time can be found like this. You write this as 2 pi L raised to half and G raised to negative half. G is raised to negative half. So 2 pi is a constant, ignore it. You write relative error in L, relative error in G. L's power is half, G's power is negative half, but always take modulus, the mod value. So always write positive value. So this is the relative error in time. Understand that. This is what you should know in terms of relative errors, multiplication, division, anything. So this is a very important rule. Okay. Many questions are asked in NEET exam based out of this. All right. Now let's come to the last part of this particular unit where we talk about dimensions of a quantity, what are the applications and uses, and how do you find it. So the meaning of a dimension, let's understand it. In the nature, physical quantity is described by dimensions. All the physical quantities represented by derived units can be expressed in terms of some combination of 7 fundamental units. This is very important. All the physical quantities represented by derived units can be represented in terms of some combination of 7 fundamental units. We shall call these base quantities as the 7 dimensions. The base quantities are called as the 7 dimensions of the physical world, and they are denoted by square brackets. So what it means is, see, for example, I take force. Can I write force in terms of fundamental? I think so. Force is mass into acceleration. Acceleration is change in velocity by time. Velocity is nothing but displacement by time. So by time over here again. So this will be mass into displacement divided by square of the time. So I've written it down in terms of the fundamental quantities. Same thing you can do with any derived quantity. You take any derived quantity, momentum, pressure, work, energy, angular momentum, torque, acceleration, velocity. All these are derived quantities, and you can always write it in terms of fundamental quantities, always. Now, these base quantities, the fundamental quantities, right? They are our there are 7 such quantities. So we have 7 such dimensions: mass, length, time, current, temperature, amount, luminous intensity. So we have 7 dimensions, right? These 7 dimensions, we denote it in square brackets with their symbol. So for mass, we use m square bracket. For length, we use L square bracket. For time, we use T square bracket. For temperature, K, not T, because then it will be confused with time. K for Kelvin with square bracket. For current, A, capital. For luminous intensity, CD. And for amount of substance, mole. Very, very important. So what are those 7 dimensions? Length, mass, time, current, temperature, luminous intensity, and amount of substance, which is basically mole. These are our 7 dimensions. Now, I know you might be thinking, sir, there were 2 more units. Sir, what about angle and solid angle? Remember, angle, dimensions of angle and solid angle, they are both equal. And you know how much it is? You know how much it is? It is this. Like, sir, what is the symbol? There is nothing in it. It is dimensionless. It is dimensionless. Very, very important. Okay. So these are 2 things which do not have dimensions in spite of having units. Solid angle is measured in steradian. Angle, plane angle, is measured in radian. They have units, but they do not have dimensions. Anything without dimensions, you just put square brackets, nothing in between that. Now, over here, can you see force is dependent on mass, displacement, and time square? So the dimension of force is the dimension of mass. Mass is in the numerator, 1 raised to that. Displacement is basically length, so length raised to 1. Time is below, so negative power of 2, so t raised to minus 2, and then complete the square bracket. So this is the dimensional formula of force. This is how it is coming. So if you know formulas in physics, you can get the dimensions of everything. And the only thing is, once you learn those chapters, you learn those formulas. So in your books, you might see big, big charts of dimensions of resistance, electric potential, inductance, blah, blah, blah. Don't get scared. Once you learn that chapter in physics, you will know the formula. Once you know the formula, immediately you can write the dimensions. Is that absolutely clear till this point? Very good. So the dimensions of a physical quantity, this is very, very important. What is the dimensions of a physical quantity? Is those powers to which the base quantities are raised to represent that quantity. Like I said, any physical quantity can be expressed in terms of fundamental quantities. Those 7 fundamental quantities are the 7 dimensions like mass, length, time, amperes, whatever. And you raise it to suitable powers and you express it in brackets to signify you are measuring dimensions. This representation is called the dimensional formula, and they are also called as the dimensions of that quantity. So all physical quantities, no matter which quantity you take, can be expressed in terms of fundamental with the help of these dimensions. They take the example of volume. Volume is side cube. Side is measured in length. So L raised to 3. Now whether you put 3 outside or L 3 inside doesn't matter. It's one and the same thing. Don't get scared. Okay. I hope this is clear. So what about time? You'll be like, sir, when I write the dimension of Sir, when I write the dimension of volume, sir, it is L raised to 3, sir. Whether I write it like this or I write it like this, it's the same thing. Sir, what about mass and time? You can put 0 also. You can put 0 also. Because anything raised to 0 is basically 1. Anything raised to 0 is basically 1. So keep that in mind. Okay. So I think we did about force also. The dimensions of force we just calculated in the previous example. M raised to 1, L raised to 1, T raised to minus 2. So this example of force, we just this particular example, we have just done it in the previous slide. All right. Amazing. Amazing. So force is not dependent on temperature, luminous intensity, mole, or even current. So those dimensions did not come. So if you are wondering, sir, where did those numbers go? They are not coming. So it is basically, even if you put A in this particular formula, it will be A raised to 0. Luminous intensity will be raised to 0. Temperature will be raised to 0. Mole will be raised to 0. So those quantities are not coming because it is not even dependent on it. It is not even dependent on it. Is that absolutely clear, my dear warriors? Awesome, awesome. Now, how do you write the dimensional formulas of different physical quantities? The best way is you know the physical quantities formula or you know the units somehow, immediately you will be able to write it down. So that is what this particular paragraph is explaining. The expression which shows the base quantities represent the dimensions of a quantity, dimensional formula, blah, blah, blah. An equation obtained by equating the physical quantity with its dimensional formula is called dimensional equation. Thus, the dimensional equations are the equations which represent the dimensions of a quantity. For example, the dimensional formula of this is this. Dimensions equations can be obtained from equations representing the relation between the quantities, large numbers. Okay. So basically, it is just telling how do you represent a physical quantity's dimension. So when I say, for example, velocity, and I put square bracket, what I'm asking you is, what is the dimensional formula? What is the dimensional formula of velocity? So velocity depends on displacement and time. Displacement by time. Displacement is length raised to 1. So displacement was in the numerator, so positive 1. By time, so times power will be negative 1. So you complete the square bracket. So this becomes your dimensional equation. This becomes your dimensional equation. An equation with the physical quantity and its dimensional formula is called as a dimensional equation. As simple as that. That is what is explained over here, not anything of very significance. So velocity, force, density, all these are dimensional equations. Now, what is more important in NCERT is this one, the section 1.6, where they talk about what is dimensional analysis and its application. Guys. Okay. Now, the recognition of concepts of dimensions which guide through the behavior, blah blah blah. A thorough understanding of the dimension analysis helps us in deducing certain relations among different quantities and checking the derivation. These are important things. A thorough understanding of dimensional analysis helps us in deducing certain relations among different quantities, checking derivation, accuracy, and dimensional consistency or homogeneity of various mathematical expressions. These are the applications of dimensional analysis, which we'll be seeing in the next few slides. You might be wondering, right? What is the use of finding these dimensions? Why did I find these dimensions? What is the use of this? The use of this is the following. We'll be talking about it. Don't worry if you're getting scared. So what does this homogeneity mean? What does this consistency of dimensions mean? What does this deducing relationships mean? Don't worry, we'll be talking about it. When the magnitudes of two or more physical quantities are multiplied, their units should be treated in the same manner as ordinary algebraic symbols. We can cancel identical units in the numerator denominator. Same is true for dimensions of physical quantities. Similar physical quantities represented by symbols on both sides of mathematical equation must have the same dimension. Okay, see, tell me one thing. When you get an expression and let's say it is like 10 meter second square divided by something like 2 uh, seconds over here, 10 by 2 you do normally, which is 5. Second cancels and you will get meter second over here. You can cancel the units, right? Correct. And say for example it is 3 Newton, 3 Newton multiplied by say 5 um, 5 meters. The answer will be 3 5s are 15. Okay, and this will be nothing but Newton into meter. You multiply the units over here. This is what you have been doing. Also, let's say for example 2 Newton plus 3 Newton, 2 Newton plus 3 Newton will be, right, or 10 Newton, or let's say 10 joules minus 2 joules will be nothing but 8 joules. 8 joules, correct? So when it is in joules, you are making sure on the right hand side also there is joules. On left hand side, if it is Newton, it is Newton. If it is Newton into meter, on the right hand side also Newton into meter. You can multiply, you can divide. When you add, don't write Newton plus Newton is 2 Newton. No. Joule minus joule is 0. No. It is just specifying the unit in which it is measured. This is what we have been doing normally in our school life. The same thing is also applicable for dimensions. So, if you ask me, what is the dimensional formula of this whole quantity on the left hand side and dimensional formula of this quantity on the right hand side, they must be equal. Same thing, the dimensional quantity over here, formula here and here should be equal. The dimension of this divided by the dimension of this should be also the dimension of this quantity. Same thing, the dimension of this multiplied by this should be this dimension. That is what they are saying. That is what they are saying. So LHS and RHS dimensions should match, number one. And whenever you multiply the dimensions inside also get multiplied. And when you divide, dimensions inside also get divided. So things like this. Say for example, m raised to 1, L raised to 1 multiplied by L raised to 2, T raised to minus 1. T raised to minus 1. What will happen? You will get basically m raised to 1, L's power with 1, L's power with 2, it will become L raised to 3 and T raised to minus 1. So normal multiplication, guys. Same way, if I write down m raised to 1, ampere raised to 2, ampere raised to 2, Kelvin raised to minus 1, the whole thing divided by A raised to 1 and let's say Kelvin raised to 1. Example. What will be the answer? The answer will be m raised to 1, m raised to 1. Here A is raised to 2, A is raised to 1. So what will be left is A raised to 1. K raised to 1, K raised to 1 will go on the top, become minus 1. So it will become K raised to minus 2. So you can just divide it normally. So this is what this paragraph is saying. You can multiply, divide. Just ensure left hand side and right hand side total dimensions should always match, or else it doesn't make sense. Now, using this, we can actually talk about something called as homogeneity principle, checking the dimensional consistency of any equation and its accuracy. So that is the first part of application, where we'll be talking about how to check the dimensional consistency or homogeneity of various mathematical equations. This is that particular slide. And in the next slide over here, after this, we'll be talking about the first application, which is deriving relations between physical quantities. Okay, so we'll be talking about that. So what is the meaning of checking dimensional consistency? It is based on a principle called as the principle of homogeneity of dimensions, which is extremely useful in checking the correctness of an equation. If the dimensions of all the terms are not the same, the equation is wrong. Hence, you know, if see what it says is, if the dimensions of all the terms which are there on the LHS and the RHS, which are being added or subtracted, are not the same, the equation itself will be wrong. Example, take this. Imagine an equation with length raised to 1, t raised to minus 2 being added to L raised to 2, t raised to minus 1. This is definitely wrong. Dimensions are not matching. I can't even write this m raised to 1, L raised to 1 minus m raised to 2, L raised to 1. Definitely not correct, because I'm subtracting two things with different dimensions. What will be correct will be L raised to 1, t raised to minus 2 plus L raised to 1, t raised to minus 2 is equal to L raised to 1, t raised to minus 2. So similar dimensions can add or subtract to give similar dimensions on the other side. I can add or subtract both. Such an equation, or that principle, sorry, is called as the principle of homogeneity. Homo means same, so similar dimensions. So principle of homogeneity of dimensions. Similar dimensions can be added or subtracted, but you cannot add or subtract different dimensions. Makes sense? How can you add velocity with acceleration? Velocity will get added with velocity. Acceleration will get added or subtracted with acceleration. Thus, velocity cannot be added with force, or a current cannot be subtracted from temperature. That is what this is saying, nothing more. Got it, my dear warriors? What is the principle of homogeneity? All right. Now, dimensions are customarily used as a preliminary test for the consistency of an equation. Okay. Now, this principle of homogeneity helps us in determining whether an equation is basically consistent. Helps as a preliminary test for the consistency of an equation when there is some doubt about the correctness of the equation. However, the dimensional consistency does not guarantee. However, the dimensional consistency does not guarantee the correctness of the equation. It is uncertain to the extent of the dimensionless quantities or functions. The arguments of the special functions such as blah blah blah, will come to it. And they go on to say that a test of consistency tells us no more or no less than the test of consistency of units, but has the advantage that we need not commit to ourselves to a particular choice of units. We need not worry about the conversion among multiples and submultiples. It may be borne in mind that an equation fails this consistency test, it is proved wrong, but it passes. But if it passes, it is not proved right. Thus, a dimensionally correct equation need not be an exact correct equation, but a dimensionally wrong or inconsistent equation must be a wrong statement. This is like studying a law book. See, if you go through this particular statement, no, your head will start spinning. You're like, what the hell is happening over here? Okay, so let me break it down in very simple words. This is why we have the decoding part. Because NCERT, the manner in which they have written is like a law book, or I don't know, some person wanted to play with kids' minds. So I'll tell you what it is. Say for example, all this paragraph, okay? This. Say for example, I write displacement, or let's say distance is speed into time. Speed into time. Is this equation correct? 100% correct. Obviously, distance is speed into time. No issues with that. If I write distance is 3 times speed multiplied by time, is this equation correct? 100% it is mathematically wrong. 100% it is mathematically wrong. Now, if you look at the dimensional formula of velocity, it is length raised to 1, t raised to minus 1. Dimensional formula of time, it is t raised to 1. On the left hand side, dimensions of distance is length raised to 1. If you multiply these two numbers, what will you get? T raised to minus 1, t raised to 1 cancels, you will get L raised to 1. Left hand side is also L raised to 1. Dimensions are matching. Here also, if you do the same thing, L raised to 1, 3 is a dimensionless number. Velocity is L raised to 1, T raised to minus 1. Time is basically T raised to 1. You multiply these three numbers, you will basically get L raised to 1, which is matching with the left-hand side dimensions. So as per principle of homogeneity, left-hand side and right-hand side dimensions should match. Similar things should be added or subtracted. So you will think that, sir, this equation is dimensionally correct. No, sir. What is wrong in this equation? Dimension wise, this is correct. That is the whole point. Just because an equation is dimensionally correct does not mean it is actually correct. That is why they are saying it is a preliminary test. When in doubt, just to check. You are seeing some options in the examination. You are seeing one option says this, distance is 3 VT. You might say maybe it is correct. I'm not saying it is entirely correct. Maybe it is correct. But imagine there is an option which goes like this. Distance is V square T. Imagine. What would be the dimensional formula on both sides? This is length raised to 1. This is length raised to 1, T raised to minus 1 whole square, and this is T raised to 1. When you multiply this, it will become L raised to 2, T raised to minus 2 plus 1 is T raised to minus 1. This is L raised to 1 and this is L raised to 2, T raised to minus 1, which can never ever be equal. So this equation is not just dimensionally wrong, but it is also mathematically wrong. So if an equation is dimensionally wrong, 100% I will eliminate that option. It can't be correct mathematically, scientifically, physically, chemically, biologically. An equation which is dimensionally correct, there is a chance that it is mathematically, scientifically correct. Okay, this is the best thing because it is dimensionally and mathematically both correct. This is what it should actually be. And just because it is dimensionally correct does not verify that scientifically it is a fact. It's just a preliminary test. Maybe, like investigations you do know, doctor will first check the blood report, blood sample. Okay, he has got this disease, maybe. This is like a small test the doctor conducted. Maybe the equation is correct. But if the test result is negative, 100% this is not possible. Okay, what is not possible? If dimensionally only it failed, this equation can never ever be true even in the dream. So this is the first application. This is that application. Dimensional consistency or homogeneity of various mathematical terms. That is what it means. And I've given examples. Consider this equation half mv square and mgh. If you put the dimensions of mass, it is m. Half is dimensionless. Velocity square is L raised to 1, T raised to minus 1 whole square. M is mass, G is acceleration, height is length. If you start putting and comparing the dimensions, you will see that the dimensions on the left hand side and the right hand side are matching. So dimensionally this equation seems right. Mathematically whether it is correct or wrong depends. Later on in work per energy chapter you will study that hey, kinetic energy can be converted into potential energy. So half mv square is mgh. Yes, mathematically also it is correct or scientifically also it is correct. So dimensionally at least it is correct by substituting mass, velocity, gravity and h value. Then in another example, uh, which of the formula of kinetic energy given below can you rule out on the basis of the dimensional arguments of kinetic energy? Now kinetic energy, okay, they have given the unit and that is basically kg meter square per second square. If you check the dimensions of this unit, kg is mass, so m raised to 1, meter is length, so raised to 2, time is second, so raised to minus 2. These are the dimensions of basically the kinetic energy. So out of the following options, by just pure dimensions, which all will not be correct? Which all will not be correct is the question. So when you think about it carefully, if you know kinetic energy formula is half mv square, so this can be correct. 3 by 16 mv square, 3 by 16 is a number, so mass into v square can be correct. But m into a, if you try it dimensionally, it will never ever be correct. M square v cube will never ever be correct dimensionally. Half mv square, okay, fine. But mass into acceleration is not the same as kinetic energy. Mass into acceleration is like force. So force can't be added with kinetic energy. So automatically option E, option C, and option A gets ruled out. Only B and D can be dimensionally correct. Out of the two, maybe only one of them will be scientifically correct, and we know by our basic knowledge that option B will be mathematically, scientifically also correct. So understand, dimensional consistency does not help us in selection. It helps us in elimination. It did not help me select half mv square versus 3 by 16 mv square. It helped me rule out which can never be correct, like A, C, and E options. This is what is the significance of this example. Till this point, everybody clear? Shall we go ahead? Awesome. Now comes the last part where we use the dimensions, where we can use dimensions to deduce relations between the physical quantities. For this, we should know the dependence of that quantity on other quantities. And for studying that, they have given one example. See, sometimes it happens, okay, sir, this force, no, I feel it depends on that speed, it depends on that radius of that ball, it also depends on that mass of the ball. But I don't know, sir, what exactly is the formula, sir, whether the force is mass into radius raised to 3 divided by length cube or something into time. I don't know, sir, what should it be? So when you're confused like that, but you know what does it depend on or have an idea, then dimensional analysis can help you. So for that, they have given an example of a pendulum. You take a thread, a bob means a small mass is attached, and you move it to one side and leave it. It will go back and forth like this. So how quick it oscillates depends on the length, on what is the mass you have tied, and the acceleration due to gravity. Length, mass, and acceleration due to gravity. What do you think the time period will depend on? So this is a very good example to understand it. So now we know time period depends on the mass, length, and the gravity, but how exactly is the formula? I don't know. So let me assume a formula, some constant into mass raised to x, length raised to y, g raised to z. X, y, and z are the powers to which you raise those quantities. I do not know what they are. So now I think, wait a minute, by principle of homogeneity, left hand side and right hand side dimensions should match, right? Left hand side and the right hand side, if I take the dimensions of this versus this whole thing, it should match. Anyways, the dimension of C is dimensionless. Oh, what is the dimension of time? Dimension of time is basically t raised to 1. C is a dimensionless number. What is the dimension of mass? That is, dimension of mass is basically m raised to 1. So raised to x. What is the dimension of length? It is L only. So L raised to 1. So raised to y. What is the dimension of acceleration due to gravity? Unit of acceleration due to gravity is meters per second square. So L raised to 1, t raised to minus 2, the whole thing raised to z. Alrighty. So what will I do now? Think about it. This will become, just normally multiply. So it will become m raised to x. Then it will become L raised to y. M raised to x, L raised to y. L raised to z, t raised to minus 2z. Combine the two, so it will become m raised to x, L raised to y plus z, t raised to minus 2z. On the left hand side, mass wise there is nothing, length wise also nothing, time wise there is 1. We know any equation which is true should be dimensionally true. The dimension should match on both sides. So naturally, my next step will be compare the dimensions. Quickly, you can see mass's dimension is 0. So right hand side x should be also 0. Here, time is raised to 1. On the right hand side, it is raised to minus 2z. So therefore, z will be negative half. Here, length's dimension is 0, and on the right hand side it is y plus z. So y will be minus z. Therefore, y will be negative of this. That means it will be plus half. Oh, so I found x, y, z, sir. What next, sir? Here is the logic. Think about it. So time will be some constant into mass raised to x. X is 0. Length raised to y. Y is basically half. G raised to z, which is basically minus half. Usually I don't write equations like this. So I'll write it as m raised to 0 is basically 1. Length raised to half. Take g raised to half below because it is negative power. So in the next step, time will be some constant. This one is 1 only. So I can just put it under the root because the raised to half means root. So time is constant into root L by G. So this is how the formula will look like. This is what dimensional analysis helped us deduce a relationship between the variables. That was that application. Okay. Now, actually, when you study simple harmonic motion oscillations, you will see the actual formula is actually very similar. 2 pi root L by G. Yes, that constant we could not find. That is a limitation to it. It's okay. But still, it is so good that I got how the final formula will approximately look like. That is the usage of dimensional analysis. That is what is mentioned in it. It is useful for deducing relation among interdependent physical quantities. But what you cannot get is also mentioned. Dimensional constants can't be obtained. This value, you could not get it. How do you know that? So you cannot get it. All right. So this is what is mentioned over here. So that was the last part. So let's come to the summary of this entire chapter. What have we done till here? Physics is a quantity science based on the measurement. Certain physical quantities have been chosen as fundamental. So first, remember at the start of the chapter, we talked about fundamental or base units. What were they? Length, mass, time, current, temperature, and amount and light intensity. So you can measure all these basic quantities in terms of standardized reference called as unit. So remember, standard reference is always called as a unit. So when I say meter, I know what is a meter everywhere, universally accepted. So standardized references are called as units, and the units of the fundamental or base quantities are called as fundamental units. So you measure temperature in Kelvin, not in Celsius. Fundamental unit of temperature is Kelvin. Celsius is a unit, but not a fundamental unit. It is a different unit. Understand that. Length can be measured in centimeters also, meters also. Meter is the fundamental unit. Understand that. Okay. Like that. The units for the fundamental or the base units are called as the fundamental or the base units. Right. Other physical quantities. I'm so sorry, guys. I gave a wrong explanation of this. Again, I'm repeating over here. Yep. So here is the thing. The units which is used to measure these fundamental units are called fundamental units. Okay. So I'm repeating, the units which are used to measure these fundamental quantities, they are called as fundamental units. Like for example, you can measure temperature in Celsius, you can measure temperature in Kelvin. All these Celsius, Kelvin, etc., they are fundamental units. Okay. Length can be measured in centimeters, meters, kilometers. So centimeters, meters, kilometers, they are fundamental units because they are used to measure fundamental quantities, base quantities. But derived quantities like velocity will be measured in meters per second. So they will be derived units. Simple. Fundamental quantities, fundamental units, derived quantities, derived units. Okay. So like mentioned over here, derived from the base quantities are expressed as the combination of the base units and are called as derived units. Like velocity, meter per second, based on two or more fundamental units. So they will become derived units. Then we spoke about also SI system, which is the most accepted system internationally. And it also includes, apart from mass, length, and time, the other units like ampere or your Kelvin or your luminous intensity, angle, everything together is there in the SI system. The SI system are used in all physical measurements for both the base units and the derived quantities obtained from them, blah, blah, blah. SI system have well-defined accepted symbols. Okay, this is standard, nothing great over there. Physical measurements are usually expressed for small and large quantities in scientific notation with powers of 10. Remember, the scientific notation which we talked about for small and large quantities, like for example, 5 kilonewton, very huge thing, which is actually 5 into 10 to the power 3, or zero point 0.6 microampere, which is 0.6 into 10 to the power minus 6 ampere. So whenever you want to express very big or small things, you express it in terms of the powers and some suitable prefixes. Certain rules and guidelines must be followed for notations of physical quantities and standard symbols. Okay, in computing any physical quantities, the units for derived quantities involves relationships are treated as though they were algebraic quantities till the desired units are obtained. Perfect. Yes. So basically what these things are saying is that certain rules which we use for the units are standard, like the kilo, micro, milli, all these things. And whenever you compute any physical quantity, the derived quantities which are there in the relationship are treated as though they were algebraic quantities till the desired units are obtained. Meaning, you can also do some things like kilo into kilo. I can write it as 10 to the power 3 into 10 to the power 3, and you can write it as 10 to the power 6. And then finally, you can write this as mega. Kilo into kilo will be mega, right? That is what it means in the end. Then the rules for significant figures and for decimal places I have already mentioned. Whenever you multiply and divide, use the least of the significant figures. Whenever you add and subtract, use the least of the decimal places. And whenever you have to round it off, see whether the last digit is more than 5, then you increase the previous digit by 1. If it is less than 5, keep the digit as it is. If it is exactly equal to 5, check the previous digit. If it is even, let it stay. If it is odd, make that odd and even number by increasing it by 1. Those are the rules. And lastly, we spoke about dimensional analysis. All those fundamental quantities have the fundamental dimensions: mass, length, time, ampere, etc. Any derived quantity, you can express it with suitable powers, m raised to something, length raised to something. And this helps us in two major things: to check whether an equation is valid or not by using homogeneity principle. Second thing, it helps us in deducing relations between multiple quantities. That is what it tells us. Okay, so that is what we have learned till now. Now, if you want to practice more questions and you want to give more tests, you already have the NEET year-long test series based out of NCERT, guys. And there are 3 modes available in it: online, that means on the computer screen at your home; offline at the center, that means in front of the invigilator, you mark the answers in a proper testing center. The last one is offline at home, that means you give the test at home on a pen and paper based kind of exam. OMR sheets are also given to you. So these 25 tests, year-long test series will continue with a proper schedule and with a proper analysis which will be followed after the test. The link for joining the test series is there in the description box below. So ensure that you click that particular link, which will open up this particular page where you have multiple options to select from, and you can hit on buy now. Okay, even if you miss a test, you can give it later on. Ranking will not come, but at least the marks will come with the analysis. I hope you guys revise the entire chapter of units and dimensions today, and if it is done, mark NCERT done in the comments below. I want to read all your comments. Thank you very much. God bless you all. Take care. Thank you for liking. Thank you for subscribing. Take care, guys. Bye bye. Have a great time. Yes, good evening. Bye bye. Take care. Hasta la vista.